Welcome back, everybody. As you remember, as we discussed in class today, we talked a little bit about some of the important concepts that you will need to keep in mind as we move forward this semester. Those of you who were not in my class, I'm sorry. These are the things that are going to be important that you will need to dig deeper into, find some help, find some tutoring, maybe even go online. Khan Academy or any of those tutoring sites and see what's going on. These are the 8 important concepts that I would say you need to know inside out, upside down. Okay, maybe not that deep of an understanding, but they are extremely important concepts. So as we work through these, I'm going to go through these 8 things today. Tomorrow in class, you're going to be doing a lab, which will help you to kind of grasp a few of the other things that are important. You're going to have to think through some concepts about the law of conservation and a couple other things. And then Wednesday and Thursday, we've got some other things to be working on. There will be another video for you to watch. I am not going to lecture in class anymore. I might answer questions here and there once or twice. I will write a few things down in class. But for the most part, your notes and your lectures are going to be digital in this format. So the 8 important concepts you need to be aware of. First one is the atomic structure. Second, kinetic molecular theory, and we're going to go through these one at a time here in a few minutes. I just list them all first, then we'll go through each page at a time. Chemical properties and changes, meaning like what is a chemical property, what is a chemical change. Chemical formulas, as in what does a chemical formula tell me about that substance. When I say chemical formula, again, we're talking about the elements and the shorthand way of describing the name of that substance. Energy, especially has energy takes place inside of a reaction. Scientific notation, which should be a review of like 5th or 6th grade. And dimensional analysis, which we talked about at the very beginning of the school year, which is again unit conversions. And finally, finding the molar mass of a substance. Finding molar mass and chemical formulas are directly related to one another. If you know what the chemical formula of a substance is, you should be able to find its molar mass. So let's go through these one at a time. First, atomic structure is protons, neutrons, and electrons. How many are inside of that atom? You need to know what an isotope is, and you need to understand that on the periodic table, the little number is not anything other than the average atomic mass. So when I say that, I'm talking about these little values at the bottom of the periodic table. So for carbon, the 12.01. What is that value? That is the average atomic mass. There are no atoms of carbon in the universe that have a mass of 12.01 AMUs. That is the average of all of the carbons all throughout the universe. Every individual atom has a whole number mass. So again, when we start to look at large quantities of atoms, that's when we start to have this average atomic mass, and that's the main idea we're looking at there. So again, atomic structure, what is a proton, what is a neutron, what is an electron? Essentially, how does those atoms stick together? That's the first thing. Second thing, not the clock. Second thing is the kinetic molecular theory. We talked about this a couple different times throughout the course of the first semester. It says that all substances, matter, atoms, whatever you want to talk about, when you get all the way down to the microscopic molecular level, all pieces, parts, are in constant motion. They move around. So solids just kind of vibrate in place. Liquids have a little bit more freedom to be mobile and moving around past each other. Gases have the most motion. They have high energies and are able to move around. The larger the mass of the sample does not always necessarily mean that it has lower energy or higher energy. Just the higher a mass would be, the more energy it's got to take to become a gas. So we're talking about the particles, and there's so many other interactive forces going on there with protons, neutrons, electrons, and how those things are being held together with intermolecular forces and bonds. So anyway, there's a lot of stuff there. Third are chemical properties and changes. So remember, a chemical property describes how that substance can become something new. How are new substances formed? The main examples we will use in our class are flammability, corrosiveness, toxicity, like will it kill me if I eat it, and the chemical stability of that atom. All of these are chemical properties. So when a substance undergoes some type of a change and it makes something new, it's because it's either burned or it's corroded or it's become toxic or through something else has become more chemically stable. So when hydrogen atoms and oxygen atoms mix together with a little bit of a spark and they go boom, it makes a more stable atom that we call, or stable molecule that we call water. The next thing is the chemical formulas. In order to do this, we need to identify what elements and how many of each of those atoms are present in a substance. So I've written here 3 different chemical formulas for us to look at. The first is called calcium acetate, and it describes the different number of each of those atoms that are found in the compound. So since calcium is written all by itself, calcium doesn't have a little subscript number right here, so there is 1 calcium atom. And the other thing is when you have a polyatomic ion, something inside parentheses, everything that's inside the parentheses is being multiplied. So yes, there are 2 carbons inside the parentheses being multiplied by 2. So in this compound, there is 1 calcium. There are 4 carbons, C2 times 2. There are 6 hydrogens, 3 hydrogens times 2. And there are also 4 oxygen atoms. So all of those are describing what is inside that chemical formula that we call calcium acetate. Underneath it, we have lithium nitrate. It has 1 lithium atom, 1 nitrogen atom, and 3 oxygen atoms, all chemically joined together to form this thing called lithium nitrate. And then the last one I threw in there just for fun because it's not something you would know how to name. This is what's called an organic compound. Organic compounds have nothing to do with no pesticides and all the stuff that we use in our everyday language. It means that they are composed of carbon atoms, and usually carbons, hydrogens, oxygens, and then nitrogens and a few of the other things can be thrown in there as well. So this C12H22O11 is the chemical formula for sucrose, table sugar. 12 carbons, 22 hydrogens, and 11 oxygens, all chemically joined together to make this sweet little crystal. All right? These are the chemical formulas. That is what you need to be able to do, is recognize when I see a chemical formula, I know how many atoms of each of those elements are found in that substance. The next thing is energy, and the biggest things about that is, do you recognize endothermic versus exothermic? You must be able to recognize the difference. Endothermic is energy going in, exothermic is energy coming out of whatever our system is. Specific heat capacity describes how much energy it takes to heat up a sample. So for water, water has a very high specific heat. It takes a lot of energy to heat it up, as opposed to a piece of metal, which has a low specific heat. It does not take as much energy to heat up a piece of metal. And then what is the difference between the terms heat and temperature? Heat is describing the flow of energy from one thing to another. Temperature is just measuring how fast those particles are moving. Remember that the definition of temperature is the average kinetic energy of the particles of a sample. We're measuring how much those particles are moving around. The higher the temperature, the more they're moving around. That's all that is. All right, that's the review of energy. Scientific notation we'll have spent a little bit of time in class today on. We use it to express large and small values, so I just wrote a few using some numbers here. So 1.23 times 10 to the 5th is the equivalent of 123,000. Sometimes we look and go, well, why would I write it in this crazy scientific notation if I could just write it like this? Well, there's other things, like if these values, those zeros that I've typed here, if those zeros were not 0, they're not necessarily going to be considered a significant digit. So scientific notation allows us to write 3 significant figures with all of this exponent saying that's how big the value is. Here's another one that's really big, 2.46 times 10 to the 8th. Essentially, that's 246 million. That's all that is. And again, it's easier to write this sometimes than it is to write out all of the zeros. So for these first 2 that were large, I used commas to help separate the space so we can count how many digits there are. But for the ones that are less than 0, like this times 10 to the negative 6th, for that, I put in spaces so you can see what's going on. 10 to the negative 6 is a very small value. It is 1, 2, 3, 4, 5 zeros, and then 4, 5, 6. If we had to move the decimal point, so here's the decimal point, we're moving it 6 places to make it 4.56. It goes 1, 2, 3, 4, 5, 6. Again, you can see that without it because of the spaces. There's 3, there's 6 spaces that we've moved to put the decimal place, the decimal point, between 4 and 5, and those spaces are just to help you see that. You don't have to do that when you write them out. You don't have to write out spaces. But it at least allows us the opportunity to recognize when we have all of these zeros, we'll put a space about every 3, so it makes it easier to count how many zeros there are. All right? Scientific notation, again, the biggest thing is it's a way for us to use 3 significant figures with really, really, really big numbers. All right? Or really, really small numbers. And then finally, we spent a lot of time in class Monday talking about dimensional analysis. We did some sample things, but I wanted to put this in your notes in case you're writing notes. Dimensional analysis is the $5 term for unit conversion. We use a conversion factor, and that factor, pardon me, that factor is either going to be multiplying or dividing to convert between measurements. I used one that we're all very familiar with feet and inches. We know that 1 foot equals 12 inches. That right there, 1 foot equals 12 inches, that is an equivalence statement. That is 2 things that are equal to each other. It is not a conversion factor. Conversion factor uses a mathematical term talking about this fraction. But these 2 fractions, 12 inches over 1 foot, or 1 foot over 12 inches, they are the same thing because 12 inches is 1 foot and 1 foot is 12 inches. But when I use these as fractions, it makes me do something else mathematically. If I wanted to know how many inches was in 12 feet, then I would take 12 feet and I would multiply it by this factor because these feet will cancel that foot. And I would have 12 times 12, right? So by doing that, 12 times 12, that's 144 inches in 12 feet. However, if I wanted to know, what if I had 12 inches, how many feet is that? That's a different movement. So we're going to take 12 inches and multiply that by this equivalent statement, or conversion factor. The inches now cancel like that, and we know that 12 inches is 1 foot because these 12 inches will cancel each other out. The mathematics behind this are what we're really looking at. What can I do to make sure that I'm understanding how to convert between different units? This becomes really important because sometimes you need to be able to cancel out the units even though you have no idea what those things really are. So we will be talking about this thing in a couple of weeks about how we determine the amount of material in a chemical reaction, and you have to be able to set these things up so that you can do dimensional analysis, unit conversion, whatever you want to call it. We need to be able to keep track of our units so that when we're done, we have the correct unit that we're trying to solve for. The last thing that you need to be aware of that we also spent a little bit of time in class on was finding molar mass. To find the molar mass, all we have to do is add up the masses of all of those atoms that you have inside the compound. So earlier we talked about calcium acetate, we talked about lithium nitrate, and we talked about sugar. So in order to find their molar mass, we're going to assume that I have 1 mole of those particles. Remember that 1 mole is 6.02 times 10 to the 23rd of those particles. That 1 mole of stuff has a mass of 158.1 grams if the stuff is calcium acetate. So 1 calcium, 4 carbons, 6 hydrogens, and 4 oxygens. If you add all of those masses up from the periodic table, you'll get 158.18 grams per mole. That is, if I have 1 mole, it's 158 grams. If I have 158 grams, that's 1 mole. Hopefully you start to see that there's this relationship between dimensional analysis and molar mass. Lithium nitrate. Lithium is 6.94. Nitrogen is 14.01. Oxygen is 16, and there's 3 of those, so that's 48. When you add those values together, you get 68.95 grams per mole. And for sugar, 12 carbons, 22 hydrogens, 11 oxygens. You add all of those up, multiplying and adding, and you get 342.34 grams per mole. Just so you know, that is about 3/4 of a pound. A pound of something is about 454 grams. So 454 grams, this is about 3/4. 3/4 of a pound of sugar is 1 mole. If you were to count out all the little particles, it wouldn't be 6.02 times 10 to the 23rd particles because the particles are actually even combined in those little crystals. So those are the big things that we need to be aware of. The other thing is this law of conservation of mass that we talked about way a long time ago. It's one of the most important laws in chemistry. We can't create or destroy atoms, matter. We can't create stuff during a reaction. This is going to be very important as we begin this first unit of study called chemical reactions. But first, these first couple of days, we're going to review a couple things. Like I said, tomorrow in class, that would be Tuesday, we're going to be doing it's called an inquiry lab. There are a bunch of things that you're going to have to be able to figure out. You're going to do two different experiments, one just burning something in the air and another where you have to keep all of your materials trapped inside of a container. And so you just need to be able to figure some of those things out. I will deliver that handout to you digitally through Google Classroom. I will also post it on Moodle so that you'll have a way to look at it as well. The lab on Tuesday should take most of the class period. There are some questions that you'll need to answer at the end of it. Those questions will be due, I believe I have said that they will be due by the end of the school day on Friday. You'll be able to work on them in class a little bit on Wednesday. I would rather get them on Wednesday. So Monday we talked a little bit about these stuff. This was your homework you were supposed to watch. Tuesday we're going to do a lab. Wednesday you're going to do the questions. We're going to kind of talk about those and start working a little bit on some Moodle assignments about reviewing of these things we just talked about. Thursday we are going to do a couple stations, and then Friday we'll wrap everything up. We'll finish up the stations as needed, and we'll begin this first unit of the second semester. Hopefully our classes will be stabilized by then, and we'll do this thing called chemical reactions. All right, there will be another video for you to watch posted here on Wednesday afternoon. Enjoy your day, and we will talk to you tomorrow morning.